All right. Another mission that I have, actually, I haven't mentioned this to the audience, but I'm actually a professor, engineering professor at Chulalongkorn University. And part of our missions is actually to create a wave of deep tech, meaning that instead of, spending less time, we actually spending longer time to groom, to create something that is difficult to replicate, difficult to copy, but also making a lot of impact. So with this mission in our mind, we'd like to show you a few things that we did in order to create this company meticulously. And some of the audience here, I hope that we could encourage you to stay in science. You saw robots, you saw a lot of things today. And this is part of the biomedical engineering, part of materials engineering, and parts of mechanical engineering. Oops. Do you have the next slide? Not this one. While we are waiting for the slides, what I was preparing for is this. At the beginning, we talked about, I think it's number 16? 16? Yeah.
Holding in your hands. Would you mind sharing with me what is it?
Oh, thanks for coming up.
Yeah, okay, of course. I would love to see that. I've been like watching downstairs all along, and I feel like this is the time. Wait a minute. It looks like is it a skull?
Yeah, this is the skull of one of our patients. And basically, we create this titanium piece that would exactly replicate the mirror image of the skull on the other side. We could also
I can hold it for you.
Okay. We could also actually create this titanium so that if the patient has a problem with the forehead, for example, we could recreate the forehead. So that it fits your liking.
Is it only for like injury purpose? How about for beauty purpose?
Okay, that's.
I think the girl would like to know, right?
That's our priority right now, helping the patients.
Okay. But beauties come later.
For plastics, we are also helping out with child that are born with defects.
Okay.
Of course, it could be applied for beauty purpose solely.
This will be a new, a great innovation for girls as well, and we are very quick about that, right?
Yeah. So, basically, what I was trying to show is first is the material that. When people talk about 3D printing, they would think about plastics. They would think about the toys, right? The machines. But actually, this titanium piece here has been 3D printed. It melts at about 1,700 degrees Celsius.
Okay.
So the melting process is actually we have to use laser to melt. So it's actually a very cool process to melt it and recreate this titanium piece. But as a matter of, because of that really high melting point, basically you are creating little welding spots, like one at a time, to create digitally this piece. So when you create things like that, a lot of things happened. There's a lot of chaos taking place. The titanium kind of shoots sparks at you, like it looks like a fireworks.
It overheat.
Yeah, like without argon control, you have basically fireworks going on. It's actually a very dangerous process. But
not a good one to see, not a Disney one for sure.
But we really spend the time to, okay, here it comes. So, thanks so much for...
Okay, so can I take this back?
Okay. Yeah.
Okay, sure. Thank you very much. I'll leave the stage to yours.
Thanks so much, guys. So I'll speed up the presentation and... give you just a few plots. This plot is called Ashby map, and it will be one of 2 plots that I'll show today, so please don't worry. This Ashby map plots the strength with the density of materials. So what you're looking at here is the bone, right? The gray spot here. It's somewhere in the middle. So if you look at the bones and you try to find things or materials that would match with the bone, as you see, the polymers are not really matching up. So we actually have to work on ceramics and metals mainly if you want to create the exact replica of the bone. And then you have to use engineering practice to bring the density down or the strength down or up. So I talked about the fireworks of titanium before. This is how it looks like, really. So we have a powder bed of titanium and the laser goes on top. How? Well, the materials is additive manufactured, 1 layer at a time. So you could create these objects 1 layer at a time. So just imagine you create it from bottom up. It's already applied in the jewelry industry, aerospace, and medical industry as Medtech is doing. The additive manufacturing process looks like this sometimes. So you don't have the powder bed, but you could also feed the materials, on the spot to create. These are turbine blades or some of the drill heads for for oil excavation, for example. The process flow is really, really simple. Basically, you start from a CAD design, and then you go directly to STL file, and then the software slides the layers, and then you start the manufacturing process. And then the last part is actually the most difficult part, the end part, which is the polishing part. We really have to spend a lot of time there, because these devices, sometimes, if you look closely, they are not really smooth. They are rough, so we have to make sure that the surfaces are adjusted towards what we need for our patients. 2012, we're not the first one. The first one was done by a Belgian doctor, and this is the first ever 3D printed metal jawbone for a patient. If you look here, there are quite a few innovations that have to take place here. If you look at the jaw, the end of the jaw, you would see that these are joints that has to be polished so that when you chew, you don't really wear away the other side of your bone. Down below, there are some holes for attaching to the muscle joints. And also, if you look at the material, it has some kind of coating. And of course, it has to be attached to sets of new teeth for this 82-year-old lady. For us, 2014, we started and completed this project. The patient arrived, this is done in Thailand by our team. The patient arrived with a type of tumor in the thumb, in her thumb, and she could no longer write. A lot of times, you kind of like live along with this, but as it affects your life, she's like only 30-something years old and could not write properly. So we have to take it out immediately. So on the right-hand side, that is the final product. But if you look closely, it's not just taking the replica of these devices. You actually have to design, if you think about your thumb, or you're playing your phone right now, like Alex does, you have to move your thumb around a lot. So the movements actually is in 360 degrees almost, times 2. So the difficult part is actually how we design the movements of this thumb so that it would be the same again. Sorry to just kidding. So we have to design this so that it would allow the lady to write again. The CT scan is one of the technologies that's given to us, available in many, many hospitals, and it's giving us the 3D file, the CAD file, like I mentioned earlier. So we take the file from the computer and do the image processing just like this. We actually do left and right, and we do the mirror image, and then we try to compare. We actually work with a lot of cadavers. In Thai, we call อาจารย์ใหญ่, so that we know that these sizes are okay, they are within the range of acceptance before we recreate the mirror image of these devices. These are some of the measurements that we made. And the process itself also looks like this. And it takes a lot of understanding as well. I mentioned earlier when we had a little bit of technical problems, these layers were created one layer at a time. So the titanium melts, goes all the way up to 1600 degrees Celsius and then down to room temperature. And then 1600 degrees Celsius and down to room temperature. So basically you are completely heating it up and cooling it down right away. A lot of residual stress, a lot of thermal expansions and mismatch in the materials. The good news is now we could achieve over 99% density with our samples. So with the right parameters of processing, we could reach almost 100%. However, if you look at these cross sections in our early days, we actually see a lot of defects. And as a researcher, we have to understand them all and make sure that none of these exist in our patients' processes. Some of the more advanced technologies include things like infrared camera to see the heat ups of the materials, to understand the melt pool. This is a dynamic X-ray image. We didn't actually do this, but we use this to understand our process. It's actually very cool. It's like really fast camera. You would see the powder lay on top, and then the laser comes down and see how it melts. If the power is too much, you actually create a hole. If power is too little, you don't really melt. So you have to fine-tune the power just of the laser. Just the power of the laser alone already gives you a lot of headache. Already a good research question. The surface itself, as printed, is actually quite rough. Some people like it for osseointegration, meaning when you inject these processes into your body, they attach well. Your bone cells actually attach really fast to these surfaces, but you don't want these rough surface when you have contacts with the other parts of the body or the bones. We also create things like different surface architecture to load the medicines to have a targeted therapeutic effects, like I mentioned before in the pitch. Or even this one, we create a foam material that we send through liquid-like blood, for example, so that we could understand how the blood and the osseointegration, which is how fast the bone cells are growing into these foam structure. With the proper foam structures, we could actually have little time for waiting. For example, when you install your dental implant, like titanium implant in your teeth, the doctor asks you to stay home for 3 months because you have to wait for the bone cells to adhere to the implant. But with this type of new technology, new surface architecture, the speed of osseointegration could reduce down to a few weeks. So, having said that, this is one of our trays that we created. So I hope that I have convinced you that in order to make all these pieces, actually it takes a lot of work. And a lot of work are carefully prepared, meticulously made, and that's why the name Meticulously. Exact measurements, the before and after, we really make sure that we have these devices after the finishing process to be exact same as the CAD file as we prepared. Well, I'd like to end here. We are hoping that we are solving some of these pain points by the doctors and by ourselves today. The first one is the availability. Many of these devices, if you look at your body, there are 206 bones in your body. Only the knees, the pelvic bones, and the elbows and some of these cranial are available right now in the market. If you break other parts of the body, you don't really have a choice. So what does it mean? The doctor actually take a pelvic bone, for example. If you break some part of your body, they will take a spare part from here. Or if you break your wrist, for example, they will take a spare part from below your knee. So, or you could take the Ajahn Yai's bone, the cadaver's bone as well, donation, which one ever you like. So right now we are exploring the unserved needs right now for all these devices that have no availability. The doctor also like to spend less time, so they are more productive. They could work with more patients. We like to free the hospital bed time and the surgical theater time. So with our devices that drop in, so there's no adjustments to be made with your body. Another problem is the standard sizing. Right now, there is a really small percentage of these devices that are designed for us Asian people. So usually we have smaller builds, and with these devices, it's your bone, right? So it's your anatomy. So no more, taking all this S size from Caucasian design. And last but not least, the support design tool. We actually work with a lot of doctors to understand their problems, and now we are aware that we are actually helping them to write papers, to rewrite their book chapters, because we are offering a completely new way to help our patients. So I'd like to end here, and I'd like to thank all these medical professionals who work with us hand in hand from all these hospitals to make this technology available to Thai people and very soon to ASEAN people. Thanks.
Thank you. I hope you will make it available to European people soon as well, because I'm really clumsy and I'm sure I'll need it soon. Thank you very much.
I'll try my best. Yes. Thank you, Adriana.
Thank you.